control systems managing fusion with impossible precision. Within hours of these findings reaching the astronomy community, NASA issued new safety protocols for Webb observations. The same instrument that peers into distant galaxies suddenly needed radiation protection when pointed at one object in our solar system. That fact alone is astonishing. Our most advanced telescope, designed to look back nearly to the dawn of time, had to shield itself from the energy of a single visitor that wandered into our neighborhood. When the world's most advanced telescope detects controlled fusion in an interstellar visitor, then NASA immediately restricts the data. You're witnessing humanity's first encounter with technology that makes our nuclear physics look primitive. Think about that carefully. For decades, scientists have worked on fusion research, dreaming of clean, limitless power. Yet here, drifting across the darkness of space, exists a machine or construct, or perhaps a natural phenomenon, that does it effortlessly. Hit that subscribe button because what I'm about to reveal will change everything you thought you knew about what's possible in space. Natural fusion requires either immense gravitational pressure in stellar cores or precise magnetic containment we're still struggling to perfect. Think about ITER, the international fusion project that's consumed billions of dollars and decades of work just to maintain fusion for seconds at a time. Human civilization has invested the most brilliant minds, staggering sums of money, and complex engineering into building a star in a bottle, and yet our success is measured in milliseconds of unstable plasma. By contrast, 3I Atlas exhibits neither condition. It's a small object with minimal gravity, traveling through near vacuum with no external power beyond distant starlight. Yet gamma-ray analysis reveals active hydrogen to helium conversion at 100 million Kelvin contained in a structure smaller than Manhattan. The magnetic fields required exceed Earth's planetary field by orders of magnitude. The energy needed would exceed every nuclear reactor on Earth combined, running continuously for decades. Either we're witnessing natural phenomena that rewrite physics or observing fusion technology centuries, perhaps millennia, beyond our capabilities. That is not just a scientific puzzle, it is a civilization-defining revelation. Natural nuclear processes follow random statistical patterns. When we observe fusion in stellar cores, energy output varies chaotically as convection currents and magnetic fluctuations create turbulence. Even our most controlled lab experiments exhibit plasma instabilities that make precise control nearly impossible. And yet, 3I Atlas's core doesn't behave randomly. Energy output varies in precise mathematical sequences, like a reactor fine-tuned by impossibly sophisticated AI. The gamma radiation pulses in complex harmonic progressions more advanced than anything our nuclear engineers have attempted. Even more disturbing, energy patterns correlate perfectly with trajectory adjustments. When the object alters course, nuclear output increases by exactly the amount needed to power those maneuvers. This requires real-time monitoring of nuclear processes at the individual atom level, something we cannot even dream of achieving. Control systems that predict quantum reactions with accuracy exceeding theoretical limits imposed by Heisenberg's uncertainty principle. Controlled fusion requires perfect balance between fuel injection, magnetic containment, plasma temperature, and heat removal. Disturb any element slightly and the reaction either extinguishes or becomes an uncontrolled explosion. Our fusion researchers struggle to maintain plasma stability in carefully controlled labs. Even tiny vibrations or electromagnetic interference cause disruptions where plasma loses confinement instantly. In space, 3I Atlas faces constant bombardment from solar wind, cosmic rays, and gravitational perturbations that should make stable fusion impossible. Yet Webb data shows the object has maintained nuclear balance for months despite gravitational encounters with Mars and exposure to solar flares. More incredibly, magnetic containment fields strengthen when exposed to disturbances, automatically compensating for environmental changes. This requires predictive capabilities that monitor space weather across vast distances and adjust parameters faster than light can travel between sensors and the fusion core. Pause and think about that. Faster than light responses, preemptive corrections, systems that seem to know what's about to happen before it does. Standard fusion follows Einstein's most famous equation, E equals mc squared. Hydrogen combines to form helium, converting mass into pure energy. The process consumes fuel at predictable rates. Spectroscopic analysis should show hydrogen depletion and helium accumulation over time. We can measure isotope ratios in distant stars with incredible precision, often determining their ages and life cycles just from subtle differences in elemental signatures. 3I Atlas, however, defies this rule. It is much closer, making such measurements routine, yet what scientists observe is something impossible. The reaction consumes no fuel whatsoever. Hydrogen levels remain constant while energy output continues at rates that should deplete any fuel supply within weeks. Imagine running a car engine at full throttle, continuously, for years, and never once having to refuel. NASA theorists propose several explanations, none aligning with known physics. The object might extract hydrogen from quantum vacuum itself, harvest zero-point energy through conservation-violating mechanisms, or somehow recycle fusion byproducts back into fuel through entropy-reversing processes. Each possibility requires physics so advanced it transcends our thermodynamic understanding. If true, these creators have solved the energy scarcity problem constraining every conventional civilization. Fusion, as we know it, produces high-energy neutrons that bombard and degrade surrounding materials. This neutron damage is one of the most critical obstacles preventing practical fusion power on Earth. Reactor components literally disintegrate under the assault, even with advanced shielding. Our best radiation-resistant alloys require periodic replacement, and no material we have developed can survive millennia of continuous bombardment. Yet 3I Atlas shows zero neutron damage despite maintaining fusion temperatures for potentially thousands, even millions, of years. Materials analysis reveals pristine surface compositions with no evidence of cumulative degradation that should accumulate over time. More shocking still, spectral data suggests the object converts destructive neutron radiation into useful energy. Instead of being damaged by fusion byproducts, it harvests them as additional power. This demands material science that either absorbs neutron damage instantly through self-healing mechanisms or prevents bombardment entirely through exotic matter properties that don't exist in our periodic table. Fusion also generates enormous waste heat that must be continuously removed to prevent meltdown. In stars, convection transports energy to surfaces where it radiates into space. In our experimental reactors, heat management is one of the greatest engineering challenges, requiring massive radiators and cooling systems. Space-based reactors face additional challenges dissipating heat in vacuum, since conduction and convection aren't possible, leaving only radiation. Traditional spacecraft work by Newton's third law. Expelling mass in one direction creates momentum change